Good morning, everyone. My name is Girish Mutreja. I am the founder and CEO of New Research and the original author of the X platform. I'm here today to talk about the 8 steps to building and deploying microservices. Effectively, what we'll be going through today is a brief recap into the what and why of microservices. We'll discuss a set of key challenges that do come with the use of the microservices paradigm. We'll do a brief introduction into the X platform, specifically around its use for building microservices-based architectures. And then the X platform has what we call the microservices model, which is building microservices in 8 steps. We'll go through that model and also do a demo. So this session that we are doing today is going to be a hands-on session in the sense that I will be doing a live demo and demonstrating a particular application in order to illustrate these concepts as well as the 8-step model. Before I continue with this slide, what I would just like to do is spin up a new environment using which we will do or run the application. The X platform allows for new environments to be spun up very easily in the cloud. And so I will just quickly spin up a new environment on AWS. What I'm doing right now is spinning up a new controller, and this controller is effectively what one uses in order to control your environment. Generally speaking, you could actually spin up multiple machines that can hook up into this particular controller, and then deploy your applications across these different machines. Today, however, we are going to use only one machine, a spun-up machine with a little bit more capacity than you generally need in order to run all the applications that we will be running on the same controller machine itself. So while this machine spins up, let's just continue with the presentation. So when it comes to microservices, essentially microservices is steeped in the same principle that was used to build the Unix operating system. And it's a philosophy that has been so successful that effectively to a certain extent it has been formalized. The Unix philosophy is, to summarize, it effectively is about taking any one particular problem and decomposing it into individual building blocks, building reusable components that have predictable input-output that you use in order to wire these components up in order to achieve the overall functionality. And the idea being is that you should do, whatever you do, you should do it in small bits and pieces, and that should be done in these components. And the components should evolve by allowing for new components to be added into the system, and rather than continuously trying to retrofit features into a single component. And by virtue of being able to wire together these functional pieces, you get a very powerful, agile, and resilient system. How does this translate to the enterprise? In Unix, if you look at Unix, it's effectively, these components are programs. These programs are hooked together using some kind of predictable input-output using pipes and file systems and input-out redirection, et cetera, And of course, the idea being is that each of these particular programs are very easily testable. This translates to the enterprise environment in the form of services. So one service, one business function, one deployment unit. The idea being is keep your services small. It should do one specific function, and that function is to do really, really well. And make that particular function an independent deployable unit so that you can actually work with that function independently of all the other functions in the system, so that your system is truly independent when it comes to these components. In order to further the cause of each of these functions, and in enterprise software, given the fact that these functions are stateful in nature, each function or each service should have private state. It is this assignment of private states to services that truly actually makes these services independent and realizes the promise of this Unix principle or the microservices architectural principle in general. So between having a simple one service, one deployable unit, one function, having its own private state, you effectively have an independent unit that you work with. And this independent unit, which is a microservice, is hooked up with other microservices using messaging. It needs to be done using provider agnostic messaging so that you can have a disparate set of messaging technologies, paradigms, and patterns at your disposal in order to allow for the system to organically grow as these services are built out and hooked up into the overall microservices environment. And finally, it is really important that in line with the Unix principle that these services, like our components, should actually be testable as quick as possible and continuously. And that is where you need this particular, these services to hook up into a CI environment, not only to be tested in isolation, but also be tested as a whole. The question is why microservices? You know, these things, it doesn't come without its own set of challenges, which we will address in just a minute. But effectively, microservices is addressing a need that has reached a sort of critical mass in the market. It is essentially around agility, speed, and intelligence. So why microservices? One, it allows for a reduced time to market through functional decomposition, through having isolated agent independence. I use the term agent and services interchangeably. You effectively can work with isolated pieces of the environment of your application without affecting the others, and therefore you do get a reduced time to market and more agility. But not only do you get more agility, you also get improved system resilience. And the reason for that is that if you have all these services that are operating effectively independently, talking to each other using messaging in a decoupled fashion, you get fault isolation. Any one particular service fails, and the rest of the system can continue, but you can get most of your functionality to continue to operate while that particular service is repaired and brought back up. Through the deployment of multiple components, you inherently get more concurrent processing, and therefore the system is inherently more scalable. So between agility, resilience, and scalability, which is the most touted set of benefits of microservices, you have a very compelling set of reasons to actually move towards the microservices architecture, which is what is compelling it to move there. However, there are additional implicit and I think more compelling reasons to move towards the microservices architecture. By virtue of this high business agility, you have continuous business adaptability. Businesses have become a lot more dynamic, and that is the reason why they're asking for more agile systems. And that continuous business adaptability is enabled by the microservices architecture by virtue of high agility. If you have the ability to be able to go from factory to floor and continuously deploy functionality and hook up all these pieces of functionality using a normalized technology-agnostic messaging backbone, you are moving information across the enterprise very easily, and that information can be used very easily. Therefore, you enable more enterprise intelligence because all this information that is now becoming available very easily fosters more innovation, and through that innovation, you allow for the information to be used in order to improve the business, and that is effectively higher enterprise intelligence. However, all of these benefits are, of course, there is a reason why the benefits exist. I mean, and the reason why these benefits are being leveraged, but it comes with challenges. If you look at microservices, closely, effectively microservices is nothing but peer-based distributed computing come to bear in mass market. Peer-based distributed computing has always existed, but in enterprises, but always has been sort of niche and depending to cater to demands of some of the niche markets like financial services, massive gaming systems, etc. Where the non-functional complexity and the non-functional demands of the system were high enough that you had to move towards peer-based distributed computing. However, peer-based distributed computing is hard. It is actually pretty hard. So obviously, we have reached a point where the business demands from a non-functional standpoint are pretty high. Their agility requirements are very high, and therefore peer-based distributed computing has become a reality. but it is hard. So before we talk about what exactly is hard about it, let me just spend a little bit of time talking about a specific application. This is the application that we will be using or kind of running today. It's a simple application. It's an application where you're actually making a pricing request, and that pricing request has to be satisfied specifically in the context of a customer. So a pricing request comes in, you need to be able to look at a particular customer, see some attributes of that customer, make a decision of what price to actually serve based on some attributes of that particular customer. This obviously has to be done in the context of reference information such as price books and offer books and catalogs, etc. In the microservices world, this gets decomposed into effectively three services, three functions. One is the pricing function, one is the customer management function, and one is the analytical function. The pricing function effectively receives the request and stores private state, which is your price and offer book or catalog, routes the request to the customer service, which is maintaining the customer catalog or the customer master, and provides an interface by which you can actually access that customer master. The pricing service uses the get customer call in order to get this customer from the customer master, and then satisfies the request by replying back to the get pricing request, and at the same time dispatches out a pricing complete notification, which is picked up by the pricing analytics service, which is holding state, which is effectively computed analytics. Now, what's important about here is that you see that there are key elements that need to be taken away from this. One is that there is private state that each of these services has, and this private state is very specific to the function that they perform. It is not shared in its data form with the other services. Secondly, the messaging semantics that you have over here are relatively varied. On one hand, you have synchronous request reply. You have asynchronous request reply, where the pricing service doesn't want to block on waiting for the get customer request to come back from the customer service. And finally, you have a pure eventing mechanism where there are events dispatched the pricing analytics service will actually pick up. These events, of course, have to be reliable. The asynchronous request reply and synchronous request reply have to be reliable so that in case something fails and something goes wrong, the system continues to operate. So if you distill out from here, what are the key elements of a microservice? Effectively business logic, the pricing function itself. State, which we already discussed, which is private in nature, attached to each or affinitized to each of these particular functions in a microservice environment. There is messaging, where you need the capability to be able to send and receive messages. A very important part, which is typically missed out when people talk about microservices and peer-based distributed computing in general, is routing. The ability to be able to make sure that information and requests are effectively and efficiently routed to the right microservices, which can get relatively complex when you have a large number of services in play. The ability to be able to manage contracts, which is the API management layer, so you make sure that your APIs can evolve so that each of these services can independently be deployed and managed in the environment. A very sophisticated monitoring and management environment is required. We'll discuss that in a minute. And finally, you need CI enablement. These are all non-trivial aspects, particularly in the context of distributed computing, which is peer-based distributed computing. However, in order to really meet the promise of microservices, all of this must be doable very, very easily and without compromising on performance and availability. That is the key challenge that a microservices-based infrastructure needs to address. So why is it so hard? As we discussed, messaging and collaboration. Messaging is a non-trivial, it's non-trivial. It may seem simple, but how to do efficient encoding, how to route, how to make sure they get exactly one delivery, to make sure that the application is not concerned about duplicates, about retransmissions, about how to work with wire formats, all that stuff is complex. State management is itself, it's hard, it is critical for the agility of a microservices infrastructure, where private state is important, but private state is not easy. It comes with its own set of challenges. Transaction management, how do you make sure that data and messaging, the integrity is maintained? How do you make sure that distributed transactions are a complete no-go? It is not scalable. So what do you use instead? There needs to be something that is provided so that developers don't have to focus on transactions. What about performance? Performance is actually counterintuitive. As your microservices infrastructure starts becoming more and more sophisticated, your performance will get worse. That's the problem with performance. Because your transactions are going to span multiple hops, multiple moving parts. And in doing so, the performance will begin to drop. So the performance requirements from each agent start going higher and higher when it comes to microservices environment. Of course, you need to continue to operate in a highly available fashion. It becomes a lot more complex when you're actually working with a multiple set of collaborating components rather than one monolithic component. And therefore, high availability has its own challenges. Error handling and operations all become a lot more complex because you have a lot more moving parts to work with. So this is effectively, by virtue of having microservices and decomposing your function and connecting them using some messaging or some kind of messaging backbone, you're introduced peer-based distributed computing, and in order to realize the benefits of microservices, you really have to make sure that the non-functional aspects are taken care of, which become a lot more complex when it comes to microservices. So why now? Given all these complexities, given the fact that peer-based distributed computing is hard, why don't we just stick with monolithic systems? Simply said, as I said before, it is because the needs for agility, speed, and intelligence have finally reached critical mass. The business needs for agility have reached levels that have never been there before. They're constantly doing testing and A/B testing in environments that are outside of development. Speed obviously continues to increase, and then this kind of breaking down the wall between the middle and back office, between analytics and transaction processing, has also contributed heavily to being able to have more sophisticated microservices and peer-based distributed computing in order to allow for the business needs to be met. So let's talk a little bit about the X platform. So the X platform is effectively a multi-agent platform for building a memory-oriented platform for building multi-agent systems. Multi-agency is our nomenclature that is being used for microservices. We've always used the term agent, and I use it interchangeably with microservice. And effectively, what the X platform gives you is a platform by which you can actually build out, very easily build applications that are based on the microservices principle. What is distinctively different about X is that it uses memory orientation and in-memory computing in a very unique way that allows for microservice-based applications to be built very easily. That's the key. So if you look at an X platform, what it does is, effectively, it allows you to be able to build out these agents. These agents are effectively message processors, which from another lens, microservices-based applications are nothing but a bunch of message processors that are hooked up using some kind of messaging, whether that be REST-based messaging or publish-subscribe-based messaging. One way or the other, you have messaging that is connecting up these message processors. What X allows you to do is actually build out these message processors very, very easily. And if you look at a message processor receives messages, does some business logic that works on state and sends out additional messages to be to be processed by other agents. X allows this to be done very easily by integrating messaging, data, and compute, which is your business logic. From a developer point of view in X, effectively a developer works on writing business logic and message handlers, works with state as POJOs, works with messages as POJOs, does fire and forget based messaging, which means that populate the message and send it out and forget about it. It will get to the destination. Update your state using POJOs and forget about it. It will make sure that it is durable. And between being able to view memory as durable and working with messaging in a fire and forget fashion, you're in a position to be able to create this very flexible microservices-based applications where you can snap these agents in and out very easily. The X platform is actually comprised of multiple modules. It caters to a variety of different use cases when it comes to microservices. The Talent module, which allows you to be able to build what we call micro apps, is focused on streaming-based applications where effectively there are data flows that you can create between that are processed by multiple micro apps or a rich data pipeline or a processing pipeline. Eagle builds on top of Talon and allows you to be able to build microservices where it tacks on things like synchronous request reply, asynchronous request reply, the REST interface, etc., on top of Talon in order to give you a microservices-based infrastructure. And then you have Robin and Lumino, which are effectively our DevOps and deployment management tools that allow you to be able to manage these applications from a centralized point of view. So X Platform, how does it actually make everything so simple? The key of X Platform is that it actually takes care of these challenges that I described as part of the challenges that come with microservices and peer-based distributed computing in general. And it makes it simple in the following fashion. Business logic is pure Java. You write business logic, and we'll see that in the sample. It is pure Java. You see no infrastructural footprint in the business logic. Messaging is pure POJO-based fire and forget. You don't actually even know which messaging vendor you're working with. We support a variety of different messaging vendors. All you do is create POJOs, send them out, register a handler, and get POJOs. State management, once again, same private in-memory POJO-based durable storage. It is completely POJO-based, it's completely private, it's completely in-memory, backed by durable storage on disk, and clustering. Transaction management is actually completely transparent to the developer. We do transaction management using a key innovation, which we call atomic event processing, which provides for exactly one's message delivery in a transactionally consistent fashion. That is transaction management, and it's transparent to the developer. From a performance standpoint, there is a lot of engineering that has gone on under the covers in order to do smart encoding, very high performance POJO generation, and 100% in-memory operation. High availability is achieved through transparent clustering. It is achieved through journaling through the use of disks in a very high performance fashion. And between clustering and journaling, you can get very, very high performance, high availability. Error handling is handled through compensating transactions, where you can do compensating transactions that compensate across multiple local transactions that operate on each of the agents. And finally, you provide a huge set of tools that allow for centralized operations from a DevOps visualization and deployment management standpoint. By being able to take care of all these things very easily, effectively what X does is it eliminates the non-functional complexity. And it is that non-functional complexity of microservices architectures that actually is the one that could compromise on the promise of microservices architectures, which is agility and speed. So by eliminating non-functional complexity, you allow the developers to work exclusively on business logic, elevating their productivity level, and from an enterprise standpoint, you allow for your system to organically grow by allowing for these agents to be snapped in and out of the network without fear and in an organic, business-oriented fashion. So let's talk about the microservices in 8 steps. The 8-step model in X, but before I go into this, I would just like to go back. Now we're getting into the point where we'll start working the actual application. I'm just going to go back and look at whether this system has come up. It looks like it has come up. I'm just going to quickly connect to it and see that. It's not fully up as yet, so let's just wait for a bit. Well, it's still coming up, so let's just wait for it. But meanwhile, let's talk about the microservices in 8 steps. So effectively, the 8-step model in X is about being able to work with the lifecycle of a microservice. And that lifecycle effectively is comprised of being able to create a service that's done very easily, to be able to manage and define your state, define your messages, write business logic. That is effectively the 4 steps in order to get a microservice up and running. And then there is the capability to be able to wire up your microservices. You know, any one microservice should be wired up with another one, and therefore to be able to land and expand in your environment. The ability to be able to test and deploy each service independently, as well as all the services collaboratively. and then to be able to monitor and control the environment. How does it happen in the X platform? Create service is done using Maven archetypes or other kinds of archetypes or templates, which give you a one-click service creation. We'll see that in action today. The ability to be able to define state. What X does is it gives you XML-based state definition. And what you do is we'll convert that to efficient POJOs through code generation. The definition of messages, which is also done in XML form, and the messages sort of serve as your contract. And that definition is done using XML, and we generate our POJOs as well as message handlers. Writing of logic, which is pure Java logic, which operates on Java-based or POJO-based state and interoperates using POJO-based messages. Wiring them up is actually done using another XML-based dependency, which is called service XML. You define service XML, so you define your contract, and you can actually define dependencies between these different services. And as soon as you make one service sort of depend on the other, it automatically has visibility into the other service's contract, and in doing so is in a position to be able to interoperate with that particular service. The ability to test and deploy, monitor, and control is through extensive capability to be able to integrate end-to-end in a CI fashion, as well as using our tools, which is the Robin tools and the Illumino tools, in order to manage your environment. So before I start on service creation, let me just once again go and check if it's running. It doesn't seem to be. I'm just going to quickly reboot this, and we'll see if it starts back up. In general, I've seen that the first time it starts up, there are typically sometimes problems, so we generally reboot it, and you only need to reboot it once. So let's talk about service creation. So I'm going to now actually start creating a service. Service creation does happen using using Maven templates. So I'm just going to quickly create a customer service. In the application that I described earlier, you have a customer service, you have the pricing service, and you have the analytics service. The customer service is what we call a CRUD service. It provides for CRUD operations on a customer object. And that is a very common type of service that exists in microservices. There is a dedicated Maven archetype or a template that exists for it. So we're just going to create the customer service right now. It's a very simple process. This can be done using the command line, or it can be done using any of your IDEs. So the customer service has been created, and so this is effectively a service that is fully self-sufficient at this point in time. It gives you full CRUD operations on a customer object that a skeleton of which is created as part of the service creation. And it's ready to go. You can actually deploy this right now, and you can do CRUD operations on the service, which we will show you how to do in a minute. But let's go back to the slide. Sorry. So that is service creation. As part of the service creation, just before I move on to state definition and, and message definition, this service actually comes ready to deploy using 3 different partitions. Each partition is configurable or deployable as a cluster. So you get high availability, you get partitioning and concurrent processing for horizontal scalability out of the box, as well as the capability to be able to have all the scripts to start and stop it in our Illumino-based environment, as well as test cases that you can use as a starting point or write additional test cases. So it is a fully baked service that is ready out of the box. Step 2, define state. In the customer service, all state is, or an X service, all state is defined using XML. And that XML is converted at build time using tools integrated with your build framework in order to convert them to POJOs. So here, for example, the state that you see is the state for the customer service. I'm not going to go into details, but effectively this state is defining a collection of customers that are rooted on a repository object and giving you an object tree, which serves as the private state for your application or for the service. This customer collection is now accessible using POJOs in the business logic, which I will talk about in a minute. Step 3 is defining of messages and defining of your API. The messages in an X service are once again defined using XML, and as is seen over here, these messages are all actually built out by the template, and you can add more of them if you like. But effectively over here, the messages are create customer requests, the CRUD operations around the management of the customer. And what is actually important to understand is that it is these messages that actually serve as the foundation for the API contract. You know, APIs from Microservice APIs that are for X services are effectively based on a DPO-based paradigm, which effectively are messages. So these messages serve as the core, as a foundational building block for the APIs of these microservices, and are actually built out in a declarative form, which are converted to POJOs. The next part of actually messaging is sort of defining your API operations. So defining your API, and we do that in the form of a service XML, which sort of serves as a service contract, of which messages are a foundational building block. So a service XML actually gives you the ability to be able to define these operations. And these operations are effectively operations that serve as your API method, and they accept arguments to be able to create customers and being able to accept inbound messages, outbound messages, the events, what the REST path is going to look like, what your REST method is going to look like, so et cetera, et cetera. It effectively gives you your entire API definition. This particular file or this XML is parsed by the application by X and converted to POJOs for use by your business logic. So just to summarize before we hit business logic, you know, you create a service, you define your state using XML, you define your messages using XML, you define your API operations using XML, hook it up into the build infrastructure using Maven plugins, and then automatically your POJOs are available for your business logic to be authored. And that's what the next step is to write your business logic. The writing of the business logic, once again, is pure Java. So I'll give you an example of one of the business logic handlers. In X, all business logic is written in message handlers. And so, for example, you have this handler here, the create customer request handler. And that handler effectively is written in pure. You'll see over here there is no infrastructural code. It is working with the POJOs that are generated by the X platform plugin. And so over here, for example, the customer object comes from state. The message object, which is customer created event, comes from the messages. So the important thing over here is that the business logic it's pure Java. And from a developer standpoint, you're really not thinking about the non-functional aspects of the application. They're all taken care of for you. Now, before we go into deployment and testing and how to manage and monitor your applications, how to kind of promote them across environments, etc., you know, right now we have talked about creating a self-sufficient service, which is one CRUD service. How do you actually now extend this to talk to other services, which is the most important part, in my opinion, about microservices? Because you can't do that efficiently, you can't get the benefit of the organically growing microservices infrastructure. So basically, the way you do that in X is, for example, the pricing service is dependent on the customer service. And that pricing service is because it's going to be interacting with the customer service. What you do in order to kind of establish this connectivity between these services is what we call peering. You basically peer these services. And you do that by declaring the service model as a peer in another service. So in this particular case, the pricing service is declaring the customer service as a peer or a dependency. And automatically, you now get visibility into all the messages and the service contract of the service that you depend on, and you can start using their messages in your service contract itself. And so in this particular case, the pricing service needs to get customer response back from the from the customer service, and it declares that it's in message for its get customer response operation that it's going to perform. And in doing so, you can actually hook up and connect up these services. Now, what's important is that purely declaratively, the system allows you to be able to create your messages, to create your state, to be able to create dependencies, other services, and hook up the build infrastructure, creates out stubs for you, and all you do is write out your stubs in pure Java. So I'm going to now go to deployment. I'm going to go back to this environment and see if actually it's going to come up. One thing which I realized I forgot to do before was, and that is kind of my bad, is actually the I forgot to punch in a couple of holes in the firewall. So let me just punch in a couple more. Sorry about that. Okay, so once I've done this, let's just go here and see if it comes up. Yes, it has. So this is basically administrative console from X, creatable using a single click in AWS, using our own AMI. Now, over here, for example, you see no systems. In the microservices world, you can think of a system as synonymous with a service. So let's just go back. I'm going to quickly build this microservice that I created. Of course, you can build this in the IDE. I just do it using So if you notice over here, there is this kind of test that is running, which is a unit test. Now they're talking about testing. Let me just walk you through that a little bit. So every application that you build, a microservice you build in X comes with its pre-baked with tests that you obviously have to build out on. But when you talk about X microservice, it effectively is comprised of a core service that is containing your state and processing of your messages and embodying your business logic handlers. And then you have a web service that you actually can hook in and talk to that particular that service using, it basically exposes the RESTful paradigm to the world. So when you want to test these services independently from an API standpoint, fully integrated or kind of isolated. And that's what X gives you. It gives you the capability of being able to launch these various components all in a single JVM, and then you can run the API testing from an API standpoint, all as a unit test. So X allows you, for example, this CRUD test is what actually does that. It does a CRUD operation test that you can build out more as you kind of build out the service. Now, what's interesting is that it allows you to be able to do a full spectrum of testing. Like, you can actually move this service from, your developer workstation, and you can move it out to a different environment. You can start doing API-based testing and then integrate it with other services and do integration testing. So that was kind of unit testing that we just talked about. The build is complete. In X, the way you actually deploy is the build actually produces what is called a jar file, which is a fully contained file with all your jars and scripts and config and everything. And you take that and you upload it into Lumina, which is our deployment dashboard. Okay, so once launched, it'll automatically appear under the Systems tab. And once it arrives in the System tab, you'll see that there are a bunch of agents that actually are part of this overall service. It is the core service, the web service, the drivers that are actually produced as part of by this template. So you'll see, for example, this customer service, and each one agent it's configured such that you can run multiple partitions, each partition primary backup. There is a driver that can drive each one of them. So it's a fully self-sufficient service that actually runs up that you can spin up. So I'm quickly going to just provision out these various agents. And meanwhile, let's just go back to the slides and see what the next steps are. So we talked about testing. We talked about the end-to-end CI capabilities. Not only do we have a unit testing that can hook into your CI framework, but also that the capabilities of X to be able to run these services in a variety of different kinds of configuration. It allows you to do API testing, unit testing, integration testing, performance testing, all of it in a very fully integrated fashion that allows you to be able to promote across environments very easily. We'll talk about monitoring and control in just a minute as soon as we have the environment up and running. So it is deployed as we see. I'm quickly going to launch out the core service, and in the interest of time, I'm just going to launch the primary. I will not launch the backup right now, and I'll only launch one instance of one of the partitions. So you can run it with a single partition, you can change configuration and run it in multiple partitions. There seems to be some kind of a problem, and that's the reason why that stopped. Don't know why. But effectively, once you actually launch it up, you can get, the service comes back up, and you can actually start testing this particular service. So Lumino is effectively a tool that allows you to be able to launch these particular services and run them in a centralized console. I'm just going to upload the other two services that we have, which is the pricing service and where is it? I'm going to launch the pricing service and the analytics service right now. I'll bring them up. And they should start showing up here in a minute. While I do that, I think one of the issues that I just encountered was that the customer service that I just built, it downloaded a new set of jars that is actually not compatible with that particular deployment, or the Lumino that we just have. So I'm just going to upload a backup version of that I had kept, just in case there were issues. And so that is, let me bring this up. And this is how you typically would upgrade a service in the environment. You just basically bring up the JAR file, upload it, it'll automatically go and upgrade the service that exists. So this particular demo customer service, I'm going to re-provision it. Provisioning in X effectively sort of creates sandboxes for these agents or these services to run, and each of the different components of the service to run. So once you provision it, the act of provisioning not only carves out space and deploys, but also deploys all the jars, updates all the config. Config is all baked in with X services, and so when you actually do this act of provisioning or upgrade, the way you work is you bake your config with your application so it's versioned correctly. So all the best practices that have gone into DevOps so far, they find their way into the way X manages services deployment. So it's deployed. Let me just see if I can launch this one. So this application, actually, the service did launch. I'm going to bring up the web service. And while it's coming up, I'm just going to set up to connect to it. So this is the reason why we actually punched that extra hole. So it's up and running. You'll notice over here that the customer service, the core service, and the web service came up. I'm just going to go here, and once the service comes up, automatically X is, the generated services are all Swaggerized. It is hooked up into Swagger and therefore auto-documented and therefore gives you a test page that you can test. So previously we ran into unit tests. Now you're promoting it to integration environment. This is how you would test it. So we bring it up. There's a demo customer service that is up and running. We can ping it in order to just test out that it's running fine. It is running fine. We'll go ahead and create a customer service and the customer. And as you see, the customer has been created. It is automatically given an ID, which is 257. And you have basically now a CRUD service at your disposal that you can actually do work with. Unfortunately, we're sort of running out of time. What I would have liked to actually show was to bring up the analytics service as well as the pricing service and sort of do an entire flow to show as to how these services are actually talking to each other. If anybody is interested in that, please do let me know. I'm more than happy to show that to you. But right now, I'm just going to summarize before we close down and start taking questions. Bottom line is that the X platform effectively gives you the capability to be able to build out microservices based applications that are multi-agent applications hooked together using messaging in a very simple, agile fashion. It has identified all the pain points that come along with building multi-agent architectures, and it has addressed those pain points by using in-memory computing in a very unique fashion. In doing so, it allows you to be able to work exclusively on business logic, has created mechanisms by which you can go from the act of creating services to deploying it and running it in production and testing it in a matter of days. To get your service up and running the first time, as we just saw, I could get up a service in about 10 minutes. So it makes it very easy to get a fully functional service that addresses all your non-functional concerns from a microservices architecture point of view and allows you to focus exclusively on business logic to get up and running and manage that particular environment in a very, very agile fashion. So with that, I'm going to close. If anybody's interested in seeing this entire flow, I'm more than happy to kind of set up some other time in order to go through it. But at this point in time, I will now take questions.
Thank you, Girish. We do have quite a few questions already, and I'm sure there'll be more coming in. We have 4 to start with, so you may want to look in your question queue, but we'll start going through these. The first question, Girish, is the person writes, Girish, I can see that X platform would be useful, but can I mix and match parts, or do we have to use it as a full stack? I'm just asking because we have a heavy investment in some enterprise tools for management and deployment already.
So the X platform is designed to be interoperable with other services written using other technologies. So for example, if you have a service that is written using, say, Spring Boot and say uses, of course, REST messaging to talk to it, but additionally it uses, say, JMS in order to communicate with other services. You could write up another X service, a microservice using X. We publish out the wire formats that we actually send out on JMS, and you'll be able to absorb messages that are sent by X, as well as there is a capability by which X can transform those messages into POJO formats for you to absorb in the X service itself. Additionally, the X service out of the box does give you REST-based communications with flexible capability to be able to manage your URL formats. So you can actually mix and match very easily. We're highly interoperable. We support a variety of different messaging platforms. We definitely support the RESTful communication mechanism. And if you create services with X, it'll interoperate with your other technologies very easily.
Okay, and the next question is, can you elaborate on in-memory model? How does the API determine what to keep in memory? How does it handle the distributed environment?
So the X platform is based on a single writer principle. The idea being is that every particular agent that is running in the system, it actually owns a piece of state. That is one of the fundamental building blocks of the microservices pattern. Each microservice owns state, and therefore it's only that particular microservice that is in a position to be able to update that particular state. If there is any information that is required regarding that particular state by other services, it is accomplished through message passing between these microservices, which is one of the reasons why message passing needs to be very, very simple, which is what X enables one to do. So, given the fact that a microservice owns its state, given the fact that that state is only visible to the rest of the world through message passing, we enforce the single writer principle in the sense that the business logic that is invoked is always invoked in the context of a single thread. None of the operations that actually is performed by X is blocking, and so therefore that single-threaded dispatch actually can perform extremely fast. Unfortunately, I didn't have time, so I couldn't show that to you, but message handler times in X, given the fact that it is local state and all in memory, is completely, is down in like single-digit to double-digit micros. So it is actually a very, very low footprint when it comes to performance, and therefore the single-writer principle works very, very well. All of state is actually held in memory. We do not actually swap to disk. We do back it by disk as a mechanism to recover from in the event of a core restart. But generally speaking, we actually hold the information in memory, in clusters, in a fashion that you don't have to actually swap to disk. We rely on the fact with 64-bit computing, you can actually hold your information in memory. And in the event that there is enough of information that you don't have memory for, the microservices can be partitioned, and the partitioning happens along the lines of state. And so therefore you slice your state across multiple partitions and use smart routing to get the messages to the right partition in order to apply it to the right state. So between partitioning, 64-bit computing, the single writer principle, and message passing capabilities, you effectively can hold everything in memory partitioned across these multiple microservices in a manner that is very, very efficient.
Thank you. That's great. So we have another question along those lines, Girish, which is, does each agent keep a complete copy of all state, or is it also distributed?
So each agent actually keeps a copy of its own state. In order to distribute state, we actually accomplish that through partitioning. So, for example, in what we just saw in this demo, the customer service can actually have multiple partitions that are deployed. If you have multiple partitions, then each partition actually holds a slice of the data. It is not the entire copy of the data. And through smart routing, using topic-based routing that we do under the covers, the information or requests to the services are automatically routed to the right partition based on the affinity of the data. So for example, in the case of a customer, you would basically partition along the lines of a customer ID. And in that particular case, a portion of customers will be held in the first partition, a portion in the second partition, a portion in the third partition. And that customer ID is also available on the sending side in order to establish the routing. So automatically on the sending side, it knows the fact that customer ID is the one that does the routing. And so therefore, it will route to the right partition depending on where that customer is stored. So it is, for each agent, it is stored entirely in memory, but each service, which can be comprised of multiple agents, are actually split and partitioned where only a portion can be held in memory.
That's great. These last two questions, Girish, are kind of around the same thing, so I'm going to combine them into one long question for you. How much faster is an in-memory architecture? Is it really worth the added effort, risk, etc.? And how long does it typically take to build your first application like you just showed?
So, well, there are two questions there. I'll address the first one. How long does it take to actually write a new application? I mean, to get an agent up and running, as we just saw, it can take like 10 minutes. You can get your agent up and running. Then the focus is completely on business logic and the complexity of the business logic, which determines how long it takes to write that application, as well as the complexity of how many other services one is interacting with, that also contributes to how long it will take. Generally speaking, what we have seen is that you can get your app up and running along the lines of the Unix principle, where you should actually be able to test your stuff really quickly. You can get your application up and running in a matter of days. It's generally, what we call the MVP, which is a minimum viable product for your application. That can take just a few days, and you're up and running and connected up to other services and talking to the other services. It is very easy to actually create services, and that's the whole point of what X has done, is to take away the non-functional complexity to make life very easy. The other question, which is about how fast is fast when it comes to the in-memory computing. Well, it depends. The thing is that the way we have used in-memory computing, by leveraging concepts of the data gravity, where function and data are always co-located, you're never actually reaching out of the process in order to touch your data. That function data gravity is actually one of the most key components to fully leverage the full benefits of in-memory computing. And in doing so, your performance is order of magnitude faster. If you're using in-memory computing and you're actually using a data store that is kept out of memory, then reaching out across the network in a synchronous fashion to get that data is going to limit your performance to maybe in the orders of maybe hundreds of milliseconds, maybe high tens of milliseconds, given the nature of concurrency and locking and a synchronous hop over the network. But the moment you actually use the X pattern of data gravity and function data co-location, you're talking about single-digit micros. So applications that we have in financial services, for example, they run in we just ran a benchmark if we can do 1 million transactions a second in sub 10 micros, and this is sort of across the network. It is only possible because of function data co-location, data gravity, and some of the machinery that's been built into X in order to allow for very high performance computing. So in-memory computing used in X is very, very fast. We're talking in single-digit micros, and coupled with all the other engineering machinery that's gone into X to make it easy while not compromising on speed or availability.
Thank you, Girish. We are almost at the top of the hour. I did want to thank everybody for their attendance today and for all the questions and interest. If you're interested in getting a trial copy or a free copy of the X platform, drop us a note. On our website, there's an area that you can do that, and we're happy to generate a key for you and get you started. So again, thank you for your time today, and we look forward to your comments and feedback.
Thank you, everyone.